Okay, guys, so here's number 4. Consider the differential equation that we've got right here. Find y equals g of x, the particular solution to the given differential equation with initial condition g of 0 equals 5. Okay, so guys, this is worth 5 points. And to get the first point, you have to separate the variables. Okay, so I'm going to multiply both sides by dx. Okay, imagine that, like multiplying both sides by dx. Okay, then I still have this binomial here that, involves y, so then I would divide both sides by this. So what I end up with when I separate the variables is 1 over y minus 2 dy equals x squared plus 1 dx. Okay, so we've separated the variables. Now we have to, so we're trying to go backwards. Dy dx, this is the derivative. Okay, that's in the middle of the derivative sequence. They're asking for y, which would be at the beginning of the derivative sequence. So we need an integral. We've got to go backwards. So now I take the integral of both sides. Okay. Now I need the antiderivatives of both sides. Are these one-step antiderivatives? Yes. Okay, so I'll be ready to take those in a moment. Is this a one-step antiderivative? No. Okay, so I'm going to have to do u sub then. So u is equal to y minus 2. du dy is 1. Okay, so I have to replace this with u's. So now this is u, this is what? Solve for dy, and you get dy is du. Okay, so the next line, write it nicely. Okay, now is this a one-step antiderivative? Yes. Okay, so I'm ready. So if you don't need the brackets, but I'll go bracket plus c, but I only need the plus c on one side. Okay. Now what goes in here are the antiderivatives. Antiderivative of 1 over u is natural log absolute value of u. And then antiderivatives here, because it's x's over there. Okay. Now in the next line, I'll put the u back in. Okay. Now I have to solve for y, but I also need to know what c is. Okay, I've also got to solve for c. So this is where you would use, this is the first time you would use the initial condition. Okay. So that's the initial condition, or the initial value, maybe I should say. I think I've been saying IV. Okay, initial value or condition. Alrighty, so I'm going to plug in 0 for x and 5 for y. So this ends up being natural log absolute value of 3. And 0 is going in for x, so is c. Guys, absolute value of 3 is just 3. So c is equal to natural log of 3. You don't need the absolute values. Okay. All right. So because of that stuff, we've got natural log absolute value of y minus 2 plus natural log of 3. Okay. All right, guys. And now, how do you cancel a natural log? You open up a base of e on each side. Okay, so cancels there. All right. So we've got, running out of room. So we've got absolute value of y minus 2 equals e to the 1/3 x cubed. Okay. I'm gonna bring in more paper. Okay, so this is where we are. Now, guys, we want to drop the absolute value bars. Okay, so I'll do it here. So when you drop them, you go, it'd be plus or minus is what you'd have to do on the right. But we have to decide, we have to use the initial condition, the initial value to decide which one it is. So, all right, so when x equals 0, y equals 5. All right, so this is from the initial, that is the initial value or the initial condition. So this needs to happen. So this needs to happen. So when I plug in 0 for x, I need to get a positive, this positive y value. So it's going to be the positive version of this. Okay, so, yeah. So y minus 2. Okay, and then finally I'll add 2. Plus 2, okay. Woo, 5 points. 5 points for that. Okay, now, part B. For the particular solution, y equals g of x found in part A, so this thing that I just found, right, this is g of x, find the limit as x approaches negative infinity. Okay, so the limit is just 1 point as x approaches negative infinity. So that should make you think of growth competition. 1/3 x cubed plus x plus natural log of 3 plus 2. Okay, so guys, growth competition. All right, so where do you see some terms where you could look at their growth in comparison to each other? Up here in the exponent. So which of these 3 terms is winning? That's a constant. So between these two, that's winning. Okay. All right. Okay, guys. Now, so think about the types of x's that you're plugging in. Okay. So you're plugging in negative x's like negative 100, negative 1,000, negative 1,000,000, negative 1,000,000,000. And when you cube those, you're still getting negatives. Okay, so this e is being raised to a negative exponent, and it's just getting huge. Okay, so let me do this real quick. The graph of this, not this exactly, but so parent function graph. Okay, so the parent function graph, y equals e to the x, whoops, sorry, looks like that. Okay, and this is an asymptote, all right? So this term here, guys, it's gonna behave the same as this graph here. And yeah, and as x is approaching negative infinity, the graph is getting closer and closer to 0. Okay, so there's other ways of looking at this, guys, but basically as x approaches negative infinity, this term is shrinking, shrinking, shrinking down to nothing. So the answer is 2. Okay, that's the answer for that. Okay, just one more part. All right, so let y equals f of x be the particular solution to the given differential equation, so the same one we were starting with, but with another initial condition, with initial condition f of 1 equals 3. Okay. find the value of d squared y over dx squared. This is the second derivative. That's what that means. Okay, so y double prime, basically. So find the value of this at the point 1, 3. Is the graph of y equals f of x concave up or down at this point? All right, so concavity. So this you need to know, guys. All right, so they're asking about f. Concave up, concave down. Okay, concave up on f would mean f prime positive. No. It'd mean f prime is increasing. It'd mean f double prime is positive. Concave down on f, decreasing on f prime, negative. Okay, so guys, they're asking us to find the second derivative, and knowing whether the second derivative is positive or negative at this point is going to help us determine the concavity of the original graph. Okay, so here we go. So here's the original derivative that we were given. Okay. Now we need the second derivative, so you have to know what that means. It means to take the derivative of both sides. So you're doing d dx on both sides. Okay. I'm going to switch to prime notation if you don't mind. All right, so this is y double prime. So the derivative of this, that's the second derivative. Now over here, is this a one-step? No, I need product rule. So d dx. Okay. Alrighty, so y double prime equals, the derivative of this part is 1 dy dx plus, okay, so the derivative of that part is 2x. So I'm going to put that in front, but that's optional. Okay. All right, now let me plug the, so what can go in for dy dx? This. Okay, that's dy dx. So let me put, whoopsie, y. Okay, actually times itself, guys, so I'll say squared. If you're not sure how I got from here to here, please pause and figure that out. Okay, so now, so y double prime at the point 1, 3 is, I'm plugging in 3 for y. So that's going to be 1 and 1 for x. Times 4 plus 2 times 1. I think I got it. 3 minus 2. Yeah, because those are 1s. And then that's 4, that's 2. Okay, that's 6. Okay, this is positive. All right, so greater than 0. All right, so I found this number, which it was asking for. Concave up or concave down? And I'll say concave up because at 1, 3, y double prime is greater than 0. Okay, there it is.